All right, I think we can go ahead and get started because it's 11 o'clock, or it's a little bit after. So our first speaker is Anthony Horsman. He's a seasoned systems engineering and project management professional and the marketing director and co-founder of UK-based LMBSE, Lifecycle Model-Based Systems Engineering, starting his career at the age of 16 as an apprentice with BAE Systems. Wow, 16 right away. He brings over 40 years of experience in the international aerospace defense industry, specializing in systems engineering for high integrity systems across the entire lifecycle. He holds an MSc in computing and technology and is both a certified coach and a PMI project management professional. He's known for his cool, calm, and engaging and pragmatic approach, often with an added touch of creative style, whilst focusing on the common sense synergy of systems engineering and project management to successfully deliver complex projects. In his spare time, Anthony enjoys travel, walking, fishing, playing guitar, I play drums, and recording. Please welcome Anthony.
We'll get the band together.
That's right.
Yeah, let me put this on here. Everybody hear me okay?
Good.
Cool. The last few come in and take a seat. So thanks everybody for coming today to MBSE-CON 25, whether you're in the room or online. It's really appreciated for you to join us. Now, when they sent out the call for papers for this, I thought, hey, I've got this idea about human interactions with AI because it's quite a nebulous thing, and maybe I should submit something. But then I saw that it was in conflict with a long planned vacation. 1 year ago I planned this. However, as luck would have it, I saw that the location was just 90 minutes from my vacation home in Palm Coast, which is just up the north of here, and not far south from the coastal town of St. Augustine. Really exquisite, beautiful place up there. Anyway, it seemed like too much of a coincidence, so I thought I'll take the opportunity and submit my abstract, and so here I am. Still enjoying my vacation, taking a slight pause. Before I go any further, a big thank you to the sponsors, to LMO, to Spec Innovations, and everybody that's pulled together and brought us together today. They've done a really great job. And also to say what a fantastic location this is. Rosen College, apparently it's the #1 college in the USA for tourism and hospitality, and #4 in the world. So as I love Florida and I'm here on vacation, I'm sure that somehow I am benefiting from this college also. Maybe next year we can do something similar on the other side of the pond. Anyway, welcome to Humane in the Loop, Sociotechnical Systems Considerations for Leveraging the Use of AI to Enhance Data-Driven Systems Engineering. I've got 2 controls here to use. So there we go. So there's me smiling up there. Oh, there's bio. I think a lot of that's already been covered. Basically, my name's Anthony Horsman. I'm the co-founder of LMBSE, that's Lifecycle Model-Based Systems Engineering. Predominantly a startup doing training and consultancy, working together also with Spec Innovations, focused on lifecycle modeling language and inner slate deployment. I'm a systems engineering and project management professional, and as you heard, 40 years experience. I jumped straight out of school as an apprentice, straight into the workshops of British Aerospace, building military aircraft, and from then progressed on into the design, test, certification, and a whole load of other stuff. So a little bit of an overview. In this presentation, we're going to explore the balance between human expertise and the application of AI in the field of systems engineering, and examine the critical role of oversight and governance in harnessing the transformative potential of AI, whilst mitigating the associated risk, highlighting the need for this close relationship between human engineers and AI, because we can't have one without the other. Well, you could, but I'm not convinced that it would work. So context with organizational work systems, a little bit of context, socio-technical systems are referring predominantly to organizational work systems that we deploy as tools of the trade within organizational projects. And thus, with the interaction between people and those technological systems, we need to recognize the importance of the human in the loop. And in terms of socio-technical systems and its integration into a functioning team environment, we need to acknowledge that the tool is really part of the problem rather than the solution. And how often have we seen the latest whiz-bang tool set rolled out as the answer to everyone's problems without a full understanding of how to harness its power within the context of the problem domain? And so those of you who are here today, I mean, if you've ever had experience of that, raise your hand if you've ever seen that happen before. They come along the latest tool set, they dump it on you, and before you know it, you've got Rational Rhapsody to make drawings that you could have done with Visio, for example. And now we've got a new quality that's been added to the tools, AI. So we need to tame that beast and get it to work for us. I think anybody who saw the previous session that was talking about the Bionic enterprise, you'll see that there's a whole lot to this that needs to be brought under control. And so this may be a new challenge in system engineering universe, but it's one for which I think that systems engineers are very, very well equipped for. And for anyone who knows me or has casually browsed my LinkedIn profile late at night or is getting on board with LMBSE, you'll know that I like quotes, quite novel, and they quite often relate to working life. And one of my favorite quotes is from Gladiator. And it says, when he's in the midst of the arena and they're about to take on the battle that they're supposed to lose, he says, whatever comes out, we have a better chance of survival if we work together. And that stands as true today as it did in the Gladiators arena. And so we must embrace AI and use it proportionately and appropriately within the context of project performance optimization, because ultimately that's what we're trying to do. We're trying to optimize our projects to get the biggest bang for the buck. And so what are we talking about here? Well, LMBSE defines model-based systems engineering as the means by which we mitigate risk, utilizing harmonized domain models to ensure the solution system is safe and fit for purpose, whilst balancing stakeholder needs and technical feasibility throughout its life. And so systems engineers are battling every day to support project delivery objectives, the time, cost, and quality, and ensuring that technical project risk is mitigated and that the end result is safe and fit for purpose. Those two things are really important. And that leads us to certification, because that's typically the end game of any of the developments that we undertake. And it's a prize that we should never forget. And in my own words, all roads lead to certification. We keep that in mind right at the very beginning. Thus, we're guided by the needs inherited not just from the customer, but from the emergent requirements of compliance and certification authority standards, which apply equally whether we use AI or not. So AI systems, what are they? In this respect, AI systems are machine-based systems engineered to achieve objectives by processing data, generating outputs, such as predictions, content, recommendations, or decisions that can influence physical or virtual environments. But it is a double-edged sword. The AI systems are now capable of doing incredible things. We know that. Complex computer chips in less than 6 hours, for example, crazy thought. A process that used to take human engineers months. And the leap in speed and capability is enabling rapid prototyping. and optimization where we thought it was unimaginable before. However, many advanced AI systems, especially those using deep learning, operate as black boxes, where it can be difficult to trace or justify critical system behaviors. And this introduces new challenges for safety, accountability, and trust in AI-assisted engineered systems. AI roles, as identified. Our new superhero team member, AI, can play a transformative role in systems engineering by enabling systems to learn from data, adapt and optimize themselves, leading to significant advantages in speed and accuracy in execution. So let's take a look at some of the roles where AI may be deployed. Firstly, predictive analytics. AI algorithms analyze large data sets to predict systems behavior, anticipate failures, and enable proactive maintenance, especially in industries like aerospace and manufacturing. An example of this is Rolls-Royce's engine health management system, which monitors thousands of aircraft engines, tracking hundreds of parameters, temperature, pressure, vibration, etc., etc. Machine learning models analyze all of the data that comes in to predict component wear and identify, for example, when turbine blades degradation is there weeks before the failure, allowing proactive replacement, so making it safer. And optimizing maintenance schedules, reducing unplanned downtime, and lowering maintenance costs by prioritizing interventions based on actual conditions rather than just simply by the schedule. And this could also lead to other side effects, such as improved fuel efficiency, for example. Detecting suboptimal performance patterns and recommending adjustments in order to maintain thrust-specific fuel consumption. So there are many reasons why these collecting of data can prove to be very, very valuable. Another area systems engineers are using is in requirements analysis. A powerful use of AI is natural language processing. We know that's one of the most common areas that's used at the moment. And if we use it to automate the extraction and classification and analysis of the system's requirements, we can improve accuracy and reduce manual effort. And an example of this, for example, is of course the MBSE tool InnoSlate, which many of us here know and love, and which utilizes language processing to assist with requirements definition through its quality score. Also, there's system optimization. Machine learning can also optimize complex systems, designs, and operations, finding the best configuration in order to improve efficiency. And overall, machine learning is revolutionizing systems engineering by making processes more efficient, accurate, and adaptive across the entire system lifecycle. However, as we move around to the human content, there are ethical and compliance concerns. Integrating AI into systems engineering tools for high integrity systems introduces challenges and demand for proactive mitigation. Primary concerns include integrity, transparency, bias, and trust. Let's take a look at each one of those in turn. Integrity. AI-driven design tools may fail unpredictably in edge cases under novel conditions, risking system failures. And many AI models lack verifiability that is required by safety standards like EN 61508 due to non-deterministic behavior. Or you may have malicious data manipulation could corrupt AI-generated designs, compromising system integrity. Or engineers may begin to trust AI outputs without sufficient validation, increasing the risk of undetected errors. Transparency. Complex AI models often lack transparency. making it difficult to audit design choices or trace errors. Where AI tools produce flawed designs, accountability may be unclear between engineers, developers, organizations, etc. Bias. So biased data sets may lead to designs that disproportionately fail for underrepresented groups, such as, for example, medical devices that are less effective against certain demographics. And optimization algorithms might prioritize cost or efficiency, for example, over other important factors. And trust. Engineers may defer to AI recommendations without critical evaluation, bypassing the ethical judgment. And over-reliance on AI tools could diminish engineers' ability to independently verify outputs. The dumbing down effect is very real and is a very real probability. Other issues other than those four may also include sensitive data exposure when training AI. If you have proprietary or safety critical data and you risk leaks or misuse. Energy intensive workflows where training large AI models for high integrity applications may conflict with sustainability goals, for example. Or legacy standards where existing certification frameworks often lack provisions for AI's adaptive nature, causing compliance hurdles. So that leads us on to what we can do in order to work together with AI as a team and utilize it effectively. We have risk mitigation strategies, and these include governance frameworks, technical strategies, human oversight, collaborative workloads, and education. So systems engineers can balance AI's benefits with its risks and ethical concerns by adopting a structured, multidisciplinary approach that prioritizes safety, accountability, and human-centric design. Governance frameworks. Implementing frameworks like the NIST AI Risk Management Framework to systematically identify, assess, and mitigate risk is recommended. And this includes governance structures for accountability, continuous monitoring, and transparent reporting. And you could also integrate ethical principles, fairness, privacy, etc., into AI design specifications, for example, bias detection tools, and ensure and reduce discriminatory outputs when applied. Technical strategies. Prioritize interpretable models like decision trees over opaque neural networks wherever possible. Not always possible, depends on the application. Simulate adversarial attacks and edge cases to identify vulnerabilities and address compatibility challenges by deploying AI in observable mode, like a sandbox situation, and thus helping to analyze the data and make sure that it's working okay without interfacing with aging infrastructure first. Don't just lob it all in there and see what happens. Human oversight, often referred to as human in the loop. This requires engineers to validate AI-generated designs or decisions for high-stake scenarios, such as medical device approval, safety-critical events, things like that. This reduces automation bias and ensures accountability. And you can also have cross-functional oversight committees that can audit AI behavior and align the outcomes with the project or organizational values. Collaborative workflows. These combine AI's data-driven insights with human contextual judgment, such as radiologists that refine AI-generated cancer screening to improve diagnostics accuracy while maintaining ethical oversight, and to continuously refine the models using real-world data and stakeholder input. Delta Airlines, for example, reduced maintenance-related cancellations significantly by iterating and tuning their predictive algorithms. And last, but by no means least at all, a very important element of any socio-technical system is training and education. So we must upskill our teams on AI. on understanding ethics, bias mitigation, regulatory compliance, etc., etc. And organizations with structured training report 50% higher awareness among engineers in these issues. Some trade-offs as examples to show what we're talking about when you bring it all together. Risk versus mitigation. So faster design optimization, which of course we all want, has a risk of unpredictable edge case failures, which is mitigated by rigorous testing and human in the loop validation. For automated decision making, that could lead to a lack of accountability and requires transparent audit trails and liability frameworks. Cost efficiency. This can lead to bias in resource allocation that requires bias audits and diverse AI training data. And all of the above require significant cooperative effort on behalf of the human element of the team in order to leverage the AI benefit, which is what we all want. Moving on to my final thoughts. AI's, I guess we could say it's a breakthrough technological component of the systems engineering tool set. So really, my objective here was not to dazzle you with data, statistics, or AI jargon. There's probably plenty of that to come over the next day or two, but to inspire you to move forward with AI adoption and to help you and your team survive, deliver in ways which may lead to project performance improvements in respect to time, cost, and quality, and ensure that the products remain safe and fit for purpose, and that certification can be assured. So with this breakthrough technology, we have these 4 areas that I would say are my final thoughts that are: acknowledge the role of AI and its impact of its failure within the context of project organizations, address the 4 areas of concerns: integrity, transparency, bias, and trust, to protect against undesirable outcomes. And last but by no means least, in order to realize the benefits of AI, a structured framework for risk mitigation should be applied to ensure there is a human in the loop. That brings me to the end. So if anybody would like to contact me to discuss things any further in relation to this presentation or what we're doing at LMBSE, you're very welcome to do so. My email address is there, and you can hit me up on LinkedIn. I guess I'd like at that point to round it off and say a big thank you to everybody, both in the room and online, for sticking with me. And if you have any questions, I'm here to ask. Thank you.
Any questions for Anthony?
More time?
Yes. Very good.
Brilliant. Cheers.
Okay, thanks.
Let me
Got about 5 minutes. We'll find next. Obviously, we're pressure wait in case some people want to come in and take the session. Yeah, we have 5 minutes. Stop.
I looked at you because I had talked to say that I decided to get one of those. I didn't have to go. Find just want to be more stressful and it's anything. Yeah. You just exist and not to disturb the peace. Of course. Yeah. Last time I had to that was and for so hot. So you can hear anything. And I got a phone call and take back to work. I'm sitting after I went to Starbucks and something and then so I was trying to like get them job electricity. So I dropped it on my lap. So I'm trying to pick it up and I can like put it up to your screen. Yeah. I would appreciate it. Glad you're right. I go line people. They're like all songs. So you're saying you can't trust anything. Yeah.
Really, you can't take it as the gospel. Why not? On the April. Yeah, right. How did you know that the engineering, the topic?
It's alive in my life.
Yeah, but stressful last like.
Yeah, I like distractions that easily thrown off by.
Yeah, no, I like that. It's everyone looking at me. That's your first drink. You know, but first to have a lot faster. It's not starting with a blank page like that. I don't know, what do we need? You know, now you can spend more time on doing what you said, reviewing it, validating it. Yeah, yeah.
Spend more time doing that.
If you spend all your time on front end, you may run out of time a lot faster. To do that. That's a lot. 10x time.
Oh, I went to Vegas for a conference in August. And I decided after the conference it was sunny out.
What I had.
So I.
An hour and a half. But at least it's like
Something better than
right.
Yeah, maybe that's like.
Yeah.
Poorly executed. Yeah.
Actually, this is fun, just terrible. Yep. Buckles.
Okay, I have 11:30, sorry.
Was not important.
So our next speaker is Mario Lopez, who is a data scientist at ManTech. He has a bachelor's degree in computer science and is currently pursuing his master's of science in data analytics from Purdue University Global. Prior to his data scientist role at ManTech, he worked for 7 years as an enterprise solution architect, supporting the Marine Corps in developing operational and system models to support capability, system, and interoperability assessments. His current work is developing AI agents and machine learning modules to support Marine Corps engineering and acquisition processes. Please welcome Mario.
First of all, I'd like to thank the organizers and the sponsors and Dr. Bieneman and Mr. Brett for organizing and bringing me in to this conference. I've definitely taken a lot out of it, and it's still very early on. I'm sure there's a lot of great content moving forward. So let's jump right to it. My work is focused on developing AI systems to enhance systems engineering. And that's my background, currently listed, and I'll rush right past that as well. I will touch on a couple of things. I did also secure my model-based systems engineering certificate for Purdue University, and I've supported the Marine Corps Systems Command and capability combat development and integration group for the last 7 to 8 years. And that's actually helped me in design the agents in a way that helps support them. Being that close to the problem when they're developing the solutions to address them really helped me get a head start on how we design the agents and the type of output we really want from them to assist our customer. So with the speed of how the enemy is evolving, with our problem space evolving, with all the solutions and problems that we're encountering, and model-based engineering is great at identifying and modeling and capturing those systems. But how do we do it faster? How do we model at the speed of relevance? How do we develop solutions and secure all the certifications and systems and all those things that you need within a capability assessment to really field the solution? And so what we do is we help our programs throughout that process. Not just through the systems engineering lifecycle, which is what we're focusing on here today, but through all the other certification processes that they're going to encounter. For Marine Corps Systems Command specifically, we think about interoperability certification, transportability, we think about safety, we think about spectrum. And these are all the activities that we've either begun attacking with AI agents designed to work on that problem set, or are still drafting, or are working to mature them. And so we have a lot of things cooking for them, and we've just done this in a short amount of time. We started the team to really attack this work that we've been contracted with at the beginning of this year. And the first thing we did was identify the technological stack that we want to host our solutions, and then how do we build them, and then how do we do the prompt engineering to really address the problem set that agent is designed to do. Additionally, we had to go through identifying the knowledge that we needed to drive that agent's logic to really provide a sophisticated level of analysis or output, depending on whatever problem we were trying to tackle. So systems engineering. Our approach was to build a community of cooperating agents with specific personas and knowledge sets and technical backgrounds and those knowledge stores that I mentioned to attack each problem individually. And the thing about the community of agents is that we didn't want one large monolithic agent that tried to do everything by itself, trying to pull from a variety of different backgrounds and contexts to do one job. You find that they are not specialized at doing anything because they're trying to incorporate too much knowledge, too much synthesis, too much processing, all in one go. And so what the industry has gone to, and what we've definitely followed, is creating a community of cooperating agents to address these problems. We have different agents with those personas specialized in different activities to really generate and synthesize a highly accurate, highly precise output to then cooperate with the other agents to begin formulating reports and outputs depending on whatever documentation or product that we're looking to generate. The two kind of approaches with managing those community of cooperating agents is through either a supervising agent that manages the interactions in the process, or through a sequential agent. And you'll use a sequential agent more with a very structured process. Say I need to take system documentation and transform it into several different products and several different outputs in a very structured approach. So then I might go through sequential to ensure that each one is cycled through. However, if I need an agent that I need to be more conversational, and you can still get the structured output out of a conversational agent using a supervising method, you can write that into the prompt, but at this point, we're using the supervising agent primarily to handle those interactions. And it really goes into identifying how we can support our customer in doing that, identifying how we can manage those interactions, identifying how what logic needs to go into each one, and creating the sequence of agents, and then building that logic into the logic of the managing supervising agent to handle all those interactions. So a lot of times we spend a large amount of our effort just building things from scratch. You know, a program office hands you a set of requirements documents, system documentation, and it's up to you to structure all that information within system level diagrams, different work breakdown structures that you have to align to. And you literally spend weeks and months organizing the information within those that system documentation. What our approach has been is to train these agents on each one of those specific products that we must generate to do those things. So all these tasks that we spend a large amount of effort, we're beginning to automate. Things like analysis, process support, document review, data generation, traceability mappings. These are all sort of core functions that we've developed agents to do at a high level. And what we can do now, because we've created these agents in a low-code solution, is actually clone the agents to be able to be repurposed for a new function. When its core task, when its core mission of the agent can be reused, we clone that individual agent so that way we're not reconstructing an agent from scratch each time we need a new one. And that's what actually enabled us to roll out and deploy agents fairly quickly, depending on the customer's needs. For instance, my Marine Corps customer, Chief System Architect of the Marine Corps, needed a faster way to develop a DODAF architecture. And he said, "Why how can we do this?" And I've been developing DODAF architecture for years, and I sat down and I started thinking about the logic for each agent, for each set of views that needed to be architected. And I said, you know, I'm designing AI agents. Why don't I have an AI agent design my AI agents? How do I intelligently design a community of cooperating agents without having to do the hard work? Because if I can avoid it, I will. And so Kevin and I were discussing this, and you know, no one I respect and disrespect more than Kevin. And I'll tell him, you know, let me just use a deep learning agent, something that can really synthesize at a high level these agents, such that I'm not really going through and manually writing the prompts for each one of these agents. I'm not manually specifying the knowledge set that each one of these agents needs. I'm not specifying what's the triggering event, what's the output, where does it need to be routed, this information to really start formulating the different set of views needed. And our use case, we're trying to develop these documents for capability-based assessments, but also interoperability certification. And so that has a lot of other connotations. So I went into Gemini, I went into its deep learning, and then I kind of just spent maybe 20 minutes writing a full detailed prompt as to what I needed out of this community of cooperating agents. And then outputted every single one of the agents I had in mind, but then it also additionally outputted agents that validated the output of the other agent to prevent hallucinations. Agents that went back and validated the output to make sure that this data was synthesized from the knowledge set that I developed or gave it, and ensure that it wasn't taking a creative approach. And the other thing that we were able to do with our agents was turn down the creativity to ensure that it was only generating knowledge from that knowledge that I provided. And then cycling it through the validation agents that I mentioned before to ensure that nothing was creatively generated. And so this is kind of a list of all the agents that are either currently under construction or near construction. And you can see the ones I mentioned earlier, specifically like program safety, integration, and then a lot of those will have sort of like the same central construct of an agent, and we'll be able to clone, duplicate, and reuse those for future usage. And the way we also construct them similarly, in the future, we have these community of agents. They're going to interact with other community of agents to really form an extensive output to support our Marine Corps customer. And so I was talking about these agents. These are some of the other ones that we've identified as the agents that we need to tackle first to really make our customer believers in the products that we're developing. These are things that we assist our customer in doing already. Now we want to assist them in doing it faster. And so the requirements analysis and generation agent is something that's actually a subset of our working group that I'll be showing you here shortly. I'll also be talking about our CJAP-C2 agent as well shortly. And then additionally, they wanted us to do the architecture agent, which I was talking about, being able to generate using deep learning within Gemini, which is hosted in the ManTech environment, and then a task or analysis agent, which is really, we receive documentation from joint programs. We have to analyze them for Marine Corps equities and return our analysis. And so these documents can be tens of pages, hundreds of pages. I used to do them manually for my customer. That was actually one of my responsibilities, was to read them, identify the Marine Corps equities, report my analysis, and then he would, as a either voting member of that working group, or within our tasker agent, would refine that output and then make the final decision. And so we also want to take that manual labor. This is a way that we're actively supporting our customer, cutting down the hours that we use to do that type of manual task and automating it for that initial output. And so this is one of my favorite use cases. Our decision scientist, Mike Jeanette, 40, 50 plus years in the Marine Corps, he provided a lot of the foundational logic for this agent. The prompt engineering is always going to take the longest because you have to identify exactly how the agent behaves. You have to validate the output, and you have to kind of cycle through that iterative process to find the prompts to really inform how the agents behave. And so with this one, it was fed Force Design 2030, Marine Corps planning, the Commandant's planning guidance, and a variety of other strategies from the Marine Corps to really inform the analysis of these solutions. So here we use fictional system data. I went to Gemini or Mesa. We have two tools hosted at ManTech capable of doing this. And I asked it to formulate extensive system documentation, but keep it in a unclassed, non-system specific format, so that way we can do our validation first before we start introducing our customer's product into that space, our customer's documentation. And so the analysis was extensive, and I think at the core of it, because we provided so many perspectives on which to analyze these solutions, we were able to have conversations with the agent. And that's the biggest thing. Like, we didn't want our agents just to be specialized at doing one specific task. Yes, we want the precision to be able to do specific output, but we also wanted to have a conversation with our agent to really be able to ask it, where did you come to this conclusion? What rationale, what logic did you use to make this decision? So right here, we have a divestment recommendation, and we analyzed a full portfolio of Marine Corps systems according to that national security strategy and that Commandant's planning guidance, and was able to start synthesizing some quality output. And so this one here shows just the generic systems with requirements and capabilities for the purpose of the conference. But when you look at the actual data, I would say it's fairly impressive when what we've output aligns with some of the strategic moves that we've seen in the news and divestment decisions in the past. So that helps validate, but ultimately we have to have those interactions with our customer to ensure that this is behaving exactly how they envision it. And that's where the prompt engineering within the agents really comes into play, because we have to iterate over and over again until it behaves the way that the customer needs it to. And so this is additional output. We moved on to aligning to the operational, the national security strategy, the conclusion, but then we also moved on to different categories: operational readiness, pursuing lethality, resilience, and adaptability, just for some other context. And we want to add additional documentation and perspectives to really refine those outputs. That's really aimed at providing a very like holistic report for high-level decision makers to really be informed about the decisions that they're making. So for this one, we also had some fun with it. I added a Google interface to go out and grab the Marine Corps budget and then kind of decompose it at a very low level to see what sort of funding the Marine Corps could use to field one of our fictional systems. And then I also told it to generate fictional data for my fictional systems based on real world systems, and to provide an approximation based off those real world equivalents, and was able to do divestment decisions, conclusions, and procurement strategies, because the Marine Corps has no money, and so we had to find ways to spend what they did have effectively. And part of it at the end of the conclusion was we recommend divesting from these certain solutions in order to invest in these, because the capabilities might be similar, or they might overlap. So that's sort of some of the output, which was great. So this is we use a low-code solution called FlowEyes because we wanted to stay away from spending all our time coding these type of solutions and spend more time on the prompt engineering and the interaction of those cooperating agents. And so that's how our typical user interface looks like when we're building these agents. You'll see the LLMs, the supervising agents, the worker agents, the tool nodes, and other different types of interfaces that our tool supports. The other thing that we've been working on is the CJATC2 agent, and this was a sort of an assessment and conformance agent to really validate whether a system was conforming to the common joint. It's a push by joint staff really to align to a strategy so that our systems are more interoperable, that they can communicate better, that they're built and structured in the same way. And so what we were able to do with this system is just introduce whatever system documentation that we had to really build that assessment report. The assessment report is very structured, very detailed, and its output shows the specific system, subsystem. You actually see it here. The citation of where you identify the feature that satisfies the criteria, conformance criteria, and then the rationale as to why it satisfies it, and then also the specific feature at a higher level, and then a confidence score, and you can actually converse with the agent more as to how it arrived at that confidence score. But this conformance report is something that was a high priority request from our customer, and we went right after it to really define those agents and prompts to really tackle the issue. So basically that's what we're doing. A lot of times my boss Kevin Brett gives me a problem and I just dive headfirst into it. I just like, all right, let me build the agent, let me not think about the design and everything like that. And it's like, no, hold your horses. We need to take a structured, rational approach to how we design our agents, and that's where the Bionic framework really helps us do that. It helps us organize the tech stack, the agent, their interactions, how we think about them, how they interact, and then we start. Now that we have this logical build in our minds, we can go out after the physical implementation, and we find that the output is getting better every single time we iterate on that agent prompt. And the other thing that I wanted to touch on was there's so much knowledge that you can gather from documentation, but there's so much heuristic knowledge that is not available anywhere, written anywhere. And what we've concluded is that you actually need to interview your stakeholders for that knowledge, to capture it, to be able to build it into the agent so that the output mirrors exactly what they need, rather than just asking generic questions to generic knowledge sets and documentations. And I think that's the critical point with where we are right now, is really iterating and continuing to meet with our customers to improve the prompts, to improve the output, to improve the reports, so that hopefully very soon our output mirrors exactly what they would expect when we're analyzing system solutions, whether it's in the systems engineering space or whether it's in any of those other spaces and certification processes that I mentioned before.
All right, any questions for Mari?
Yes.
Yeah, so you kind of ended there, but I'd maybe expand on a little bit. Using the AI agents to do sort of design review, I would think in some ways it's probably more thorough than human. But what's been your experience in terms of, making sure you entrance criteria, success criteria are set?
Our experience is that it's been fairly accurate in analyzing them. The rationale is there, the output's there, it's not dropping data, but at the end of the day, it still needs that validation and precision from ourselves first,
That's
and
what
then
I
our
wondered,
customers.
check the box that it was delivered, but not evaluate whether the answer really answer the question, which is where the speed kind of comes.
Yes. Yeah, so that initial data generation, I find it very helpful to really get the baseline constructed, and that might shave off like weeks or months depending on the size of the system or the amount of documentation you have to sift through. That'll shave off months off the front end. And then we can focus more on the back end where we need the precision, where we need the specificity, where we need the customer validation. That allows us to invest all our time in making sure that is absolutely right. When I'm developing DOF architecture, or when I used to, for both CDNI and systems command, a lot of times we spend weeks and months developing the initial documentation just to have the conversation about the system. Depending on the complexity, like CAC2S, which is the ACAT1 large program. And what we've done now with the DODAC agent that we constructed is we can feed whatever type of system documentation you have, capability document, ICD, CONNET, interface control document, and we develop a full baseline of architecture products developed directly from their documentation, so that way we can have a conversation as to what their diagrams, what they're actually saying in their diagrams. So a lot of times they'll look at your diagram and say, this isn't correct, and then I'm able to ask the agent, well, we generated this specific exchange, this is specific subsystem from line such and such on page such and such from your system documentation. And so that helps them develop their documentation as well as improve our model. And meeting back and forth between them, our models improve and their documentation improves.
Are you getting the agents to actually be able to interpret the diagram?
The diagrams?
Yeah.
Right now, I don't have the visual processing on that yet.
I didn't think that.
We're working.
I mean, when that comes up, great. I didn't think we.
Yeah. We have matrices. We can process matrices and tables. But the diagram, the image processing, that's still work in progress. And eventually we want to get to the point where we do the output as well. But that'll take.
And we're looking at like setter events too. First, every setter event is like a collection of products, whether they're documents or models, right? So you've got to review all of that stuff, and all the different C's, look at each one that they care about from their perspective and so on. So I mean, that alone is huge. You think about, that engineering V and all the setter events that would typically happen in like a size program. Like, holy cow, right? But if you can at least get to the point where you're producing that information, the models, and even if you still want to have documents, you can still produce some of that. That, like Mario said, if you could say that's on the front end though, that gets you further down the field a lot faster. So you're not creating, you're spending more time reviewing.
And eventually we want to get to the point where we're also doing system model and handling them in the same manner, where we have a firm whole grasp on how the DODAP architectures are constructed, and now we're trying to we will be building that logic to give you that initial system level like breakdown.
You're not allowed to say system in this room.
Oh, sorry. We eventually want to generate, if we can't do at least the images, at least the systems and the exchanges and what they exchange, and if it's in tables, we can import it. So that's where we bring in our Canada tool and do the modeling. Yeah.
You said just fairly briefly touched on it, that
implemented basically a Google feature in your in one of your agents to pull information about the budget. I want to know how flexible that Google tool you used was, and was it able to only take specifically the budget information, or were we able to query it on basically whatever relevant information you wanted? And were you worried about that poisoning the well, so to speak, because the hyper-specific agent specificity that each small agent was designed for? Because once you open up that floodgate of being able to pull in all information from essentially the entire web, how are you able to say that this information that the agent is providing is now solely based off of whatever your input was via that kernel or the documentation that you fed it originally?
Right. So we built an individual agent that had the tool set to be able to search the internet to return that information. I don't believe I directed the agent to redirect that information to our data stores or vector stores, where we generate the system documentation and output. Its purpose was solely to be able to return that information. So in my supervising agent, you have to put the logic in the supervising agent. When your user prompts you for this question, you route to this agent to return its output. And so I think I handled it that way. Now, ideally, what I would do is route that agent through another validation agent. But like I said before, the information it's retrieving is not going into our vector stores or data stores. I didn't build that interface for it to do that. Not saying it can happen, and we'll definitely have to test and validate to ensure that's not happening. But that's definitely a risk that you run as soon as you build an interface to the internet. Yeah.
None of this is possible, right?
No. So
Better not be.
It is.
So everything we built was either strictly fictional, that we literally generated with AI, like generate me a fictional CDD, fictional concept, fictional PSTEC requirement. And then any documentation we ran it again is publicly available, not CUI, not unclassified, definitely not classified, or else I'd be probably pulled off the stage right now. So, any other questions?
We're right on time.
Cool. Thank you. Thanks, everyone.
Thanks. Okay, our next speaker is Dr. Jerry Sellers, our reigning champion of trivia. He's the author of Understanding Space, An Introduction to Astronautics. Good book, I've read it. Contributing author and editor of Applied Space Systems Engineering, another good book that I read. And a contributing author of Human Spaceflight Analysis and Design, which I haven't read. He has over 40 years of experience, systems experience, including guidance and onboard navigation, officer in Space Shuttle Mission Control, assistant professor of astronautics at the U.S. Air Force Academy, and chief of astronautics for the Air Force European Office of Aerospace Research and Development. He is an associate fellow at AIAA and the former chairman of the Space Systems Technical Committee. Jerry is a certified Scale Agile program consultant and a corresponding member of the International Academy of Astronautics. He is also an adjunct professor at Stevens Institute of Technology. Please welcome Dr. Sellers.
You just click this way. Okay. Hey, good morning, everyone. How you doing? I'm Jerry Sellers. Thanks for the intro. There we go. There we go. That's me. We just heard about me. My co-author is Shannon Kimball. She's not here today, but she hopefully developed some of the material here that we're going to be talking about. I'm not talking about AI. We have two talks on AI. My AI talk's tomorrow. I'm going to talk about the old kind of intelligence, which is the old-fashioned kind. As we look at that, where do we go here? That last mile or that first mile. So it's often said that in project that the last mile is the hardest. But I think my experience here with, especially with MBSE, is it's the first mile that can be the struggle. How do you get people started? And that's what we're going to talk about today is our experience and how do we get people started on this. So a little bit of background on what led us to this, kind of the approach we take, and the results and conclusions. My company is TSTI, Teaching Science Technology. We're one of the sponsors. We have a booth over there if you want to come by and talk to me or Amanda. We've got some cool swag, so come get some of our swag. But we've been in business about 30 years doing consulting and training in primarily space industry, but outside space. In fact, one of the examples we'll be talking about today is actually a Navy example. But we do teaching and training all over the industry. If you're interested, come by and talk to us at our booth. I'm preaching to the choir here. I know about model-based system engineering, but one of the books that Randy mentioned is Applied Space System Engineering, and we have a chapter in that book on MBSE. And as we're developing that chapter, kind of in the context of all of system engineering, we came up with what are the benefits, really the value proposition for MBSE. And in that, we came up with what we call our 6 C's. And the 6 C's there, you can read the long definition or just look at the diagram there. But we say the 6 C's of model-based system engineering is the ability to capture, connect, and communicate. I usually say those are the first big important 3. Capture information, connect information, which would otherwise not be captured or be captured in somebody's head, and then put it back out to communicate, right? If all I do is capture it, then it's just a black hole of information. I want to be able to put it out to communicate that. Once I can communicate it and have it in a one integrated place, then I can support and enhance collaboration across the team, control, which you can think of as configuration management. And then I always use a little Agile symbol there, although you don't have to be Agile, but this ability to do a tight turn. I'm always nervous when people say MBSE is going to save time and money. Maybe, more likely not. Because work always expands to fill the time, but the time spent is going to be more effective, and the ability to turn data faster is something that I think is a big benefit. It's hard to quantify the cost of that, cost savings of that benefit, but definitely a benefit. But those are the things that we see as our key benefits of MBSE. And Warren Benevin, who talked here earlier this morning, came up with this model for really, what do you need to get MBSE going in an organization? And the hats off to Warren, because I think he did an excellent job of really crystallizing what are the key elements, the key puzzle pieces that we need. And we teach system engineering all over the industry. And this is one of the big diagrams I always show as we get started in MBSE. What do you need first? Well, first of all, you need to be able to understand systems engineering. Right? And that seems trivial, like, oh, of course I need system engineering. But what I often find is that trying to employ MBSE in an organization highlights system engineering ignorance. And they find out, oh, you got to go develop a functional architecture. Oh, what's that? Like, well, if I don't know how to do it on paper, I can't do it in the model. So system, structure, modeling language, architecture, and getting started is where we tend to fall. We're going to, later on today, I'm going to talk to you about the architecture piece and lifecycle modeling framework. But here we're going to talk more about the upfront piece that we need to be able to do effective MBSE to kind of get people started on that whole thing. And that challenge then is, how do I really get take these puzzle pieces apart, and how do I get started on that system engineering side, the system engineering puzzle piece, so that I know how to be effective. What I've seen, and maybe some of you have seen this too, I've seen some ineffective rollouts, ineffective implementations of MBSE. And the tendency then is to say, well, it's the tool, it was a bad tool. Let's blame the tool. It's not the tool, right? It's the people, it's the process. And if you don't have a process for doing requirements development and management, that I have to teach people that the tool is not a process. And the tool is just that. Tool can support a process. Tool can be part of the process. The tool isn't the process. Humans are the process. And how do we effectively integrate humans and the tool together to create that process? So what we're trying to do here in this discussion is look at how do we get people sensitive to that, and how do we set them up for success if they want to go on to do an MBSE implementation. our goal, in the whole world of digital engineering is how do we take this laundry list of typical, contract deliverable items, procedurals, how do we take all that laundry list of, paper-based world and distill it into key deliverables? And as an educator, as a trainer, we always figure our job is to take the complex and figure out how to make it simple. Not to dumb it down, but how do we take complex ideas and complex problems and explain it in ways that people who are especially first getting started on it can understand it. So what we did is we took this whole area of both project management and system engineering, because it's hard to really decouple those. And that's one of the things I like about the idea of life cycle modeling, is it includes elements of project management that are important to realize that you can't always take away from the system engineering. So these are all the typical project management and system engineering deliverables that we have. And what we did is try to boil those down to a key set of deliverables. So we ended up with 28 separate deliverables, artifacts, if you will, that are important for project management and system engineering. And our original motivation for this is that we do a program, we do a course for NASA called Project Management and System Engineering. It's a 8-day class that does both. And of course, it's a tall order to teach both those topics in only 8 days. But we do that by distilling it down, looking at what are the key elements, the key takeaways that we need. And we came up with a set of deliverables that I'm going to talk about. And this is part of our, we call it a project accelerator here, to get people focused on the key things. Here it is shown in a swim lane version. My Navy colleague calls this his chiplet chart. But it's what are the key things that you need to do. And so he'll show this on all his projects and say, okay, folks, we got to do these things. And so for the projects that I'm going to talk about here, we gave this to the team and said, okay, here's what we're going to focus on initially to get going. And then we can further boil that down. So we had 28 separate deliverables, and we boil that down to stories. So we use an Agile approach to do this because Agile is nice when you got a few people together in a room for a short period of time. Not that you have to go be Agile for the rest of your life, but Agile is a nice approach for getting a lot of things done in a short time. And one of the things that I like about Agile is let's come up with a story, right? And that story describes the task, and the story defines not Department of Defense, but a definition of done, DOD, for that. And so we say, okay, here's our story. As a system engineer, I want to know the as-is operational architecture, or we went over to, so that I understand the legacy context. So your task is to come up with the as-is context, assuming there is one, and develop the operational interfaces for that. And then we have our definition of done that comes out of that. So we kind of give this then as stories to the group, and then here's another description of that. And we broke it down into system engineering and project management artifacts, and then further broke down system engineering into con ops requirements, etc. And so here you see another example. So preliminary level 1 requirements, there's the story definition, there's the task, go develop your level 1 requirements, and then definition of done, requirements are validated, well organized, and traceable to the project goals and objectives. They've been reviewed and accepted by the product owner and the business owner, and they're ready for decomposition to level 2. So this is telling people, hey, here's your task, here's what you got to do, this is what done looks like when you get there. And one of the things that always surprises our students as we're doing this in our actual exercise and workshop is how much time it takes to get coordination. So people always forget that, it's one thing to develop the artifact, it's another to get it coordinated and approved, right? And that's where actually most of the time ends up being sucked in. So that we break that out, and that becomes this is what we hand the people in our workshop to go forth and do. And then when we do it in a virtual basis, we actually use a Kanban built into Microsoft Teams, working this in a virtual environment. In a live environment, we do it with sticky notes on a board, and we do it with flip charts because it's more tactile to be able to touch a flip chart and look at that. So here's how we do it. And I said there's 2 different workshops that we do here. I'm going to address. The first is one where we do with NASA. It's called a Project Management and System Engineering course, and it's an 8-day focus course. And in there, So in that 8 days, we give them lectures on project management, lectures on system engineering, some of that sort of just in time. So we talk about requirements, and then they learn about, how to do requirements, et cetera. And then we give them a big project. So they have about 12 hours in that 8 days to work on a project. And we break them in. We kind of use a NASA approach where we have a program office with a NASA is called a highly coupled program, where you have separate projects that are highly coupled. And the program we use is called AWARE, and it's basically, how do I go out and detect forest fires for the Forest Service? So the Forest Service is our customer, is our key stakeholder, and then we give them the FireSat project. So if anybody's been around the space industry very long, you've heard of FireSat. We say it's most famous mission that's never flown, because we use it for examples all over the place. So we give them FireSat as one project, and then we give them Fire Falcon, which is think of a UAV-based set of UAVs to go out and monitor fires. And then we have operations. We have 3 projects: FireSat, Fire Falcon, Mission Ops, and then we have a program office that oversees all that. So we break them into teams, so roughly 6 or 8 people per team, right? So different offices that they work in. We give them that backlog that I just showed you, those 28 items, and we say, okay, go off and as individual projects, figure out all these things, your requirements, your ConOps, your integrated master schedule, et cetera, as projects. But oh, by the way, you have to integrate that as a program, right? So then you have to do all of that as well. So they're developing paper products for that. For NASA, we don't have time to do MBSE because we only have 12 days. So we will have them do paper products for that. And then we use an Agile construct. So if anybody's familiar with Agile, you talk about sprints. A typical sprint is 2 weeks in Agile. We have 2 hours. And so we do a 2-hour sprint. And in that 2-hour sprint, you say, here's your backlog. Okay, get ready for your backlog. Go work for 2 hours, basically blow the whistle. Okay, go get going. And then at the end of 2 hours, pencils down. And now let's all go compare what we did. And it really, there's an old saying, goes back to the 70s, that as a project manager, there's only 2 things you can manage: time and tension, right? And that's what we're managing here. So we give them a specific amount of time, and the tension is basically, well, these are the things you have to produce. And it tends to really focus. We started going to an Agile approach on this project and this course, this workshop, probably about 8 or 10 years ago. Before that, we didn't do that, and it was not nearly as effective. So really managing the time and tension through this Agile construct gets them going. Having the backlog gives them focus, and then they can go forth and start developing the artifacts. So that was the one project that we do, the Project Accelerator. That's with NASA, Project Management System Engineering course. The other thing we do is called a Project Accelerator Workshop. This is what we've mainly done live. I think we've done it virtual 1 or 2 times. So this we did with a Navy customer. I was going to have my Navy customer as the co-author, but as you guys know, it took them so long to get approval that they just said, nah, so I've got some quotes from them, but I won't mention the project, but it doesn't really matter. But so there's a Navy project that we supported, still ongoing. And they brought us in actually late last year to help them. So we brought the key stakeholders for the project into the room. It's a multi-million-dollar program Navy's doing. Key stakeholders into the room. And we did the same sort of thing. So we did 2-hour sprints in the room, and we broke the groups into teams, not project program office, but more like your requirements, your ops, your logistics, et cetera. And then we worked the same artifacts divided up differently, but we still did it in this sort of Agile approach. So we blew the whistle, go get work for 2 hours, come back, compare notes, rinse and repeat. And that's a good effective way to make a lot of progress in a short amount of time. So those are 2 big projects that we set that on. One of the things, of course, is getting approval, and so having a process for how you close the loop on the artifacts you're generating. So again, here we're developing paper products, but what we did in the Navy, we don't do this with NASA, but with the Navy, what we were doing is actually modeling in parallel. So they were creating paper products. I'll show you some examples of this in a minute. They were creating paper products, but then on the side, we had some folks over here modeling. And so then we would put it into the system model, and then we can put that back out to the stakeholders and say, okay, this is what you told us on paper. here's what it looks like in the model. What do you think? Right? And then oh, well, actually we missed this, we missed that. All right. So that worked out actually very effectively too, doing modeling sort of in parallel in the background, kind of model following the intellectual development of the information. This is what we laid out for the NASA folks here just recently when we did this, to show them what's their sign-off process. So, okay, you're going to develop initial artifacts. How do I get it signed off? How do I get it approved? How do I get it reviewed? Right. So what's that review process look like? And it's, at any point you may get stuff kicked back, or, on purpose, we created this idea that you had to, have integration across teams, and you may get up to the high level and figure out, hey, my understanding of the ConOps is different than the other team's understanding of the ConOps. Okay, we got to go back to square one here and get realigned. That's reality of life. And how, system engineering is always 2 steps forward, 1 step back, right? It's how it works. And so we have to teach that, just because you have a bright idea doesn't mean it aligns with the other team, and you got to figure out how to get that cohesion across the teams. So these are the kind of other products that they created. So this is back on the NASA project. So they created, again, paper products, PowerPoint version, PowerPoint engineering, but getting them to apply what we teach about system engineering, project management. So in this case, here's how do you come up with a kind of a data flow for we've got our fire sat, we've got our Fire Falcon out there doing things, and how do they coordinate with the ground systems? How do they do a data flow diagram? So, one of the products we asked for is a data flow diagram. So how does the data move through the system? What does that look like? So again, PowerPoint engineering, but we're trying to get them to think about the concept. And then if they can do it in PowerPoint, then, I always say, if you can't do it on paper, you can't do it in an MBSE tool. If you can't do it on PowerPoint, you probably can't do it in an MBSE tool. So how do we get them thinking about the basic products? There's an example of the stakeholder context diagram we might have them do. So again, thinking about how the stakeholders relate to the project. Here's an example, another example of the data flow diagram they did. So showing how the FireSat space segment interacts with the Fire Falcon, and how all that flows eventually back to the user. So getting them to apply what they learn within the context of the course. I say, system engineering it's not a spectator sport. You got to get out and kick the ball around. And this gives an example of how they can go out and kick the ball around for an artificial project, in this case, FireSat. But then it works just as effectively for a real one. So for the Navy project, again, it was a cool sight to behold. We had like 30 people in the room, different parts of the room about this big, flip charts, all over the place. It warmed my heart as a system engineer. The folks working on requirements had 4 easels set up, and they were doing form, fit, function, feature on each easel, writing requirements. It brought a tear to my eye. It was great. And then we had folks over on the other side working on ConOps, and we had, the real subject matter experts in the room. We had, chief petty officers who were actually doing maintenance on the system, saying, well, no, this isn't how it works, or no, this is what you got to do when you're on the ship. And that was feeding into their understanding of the ConOps and the system architecture. We had the folks who are actually building the system in the room and the customer in the room, and finding out that, guess what, on the bill of materials for the people who are building it, they use different terminology than the folks who are doing the system architecture. Who would think, right? So simple things like, hey, you call it X and we call it Y. Oh, I guess we should come up with a common name for that thing. Okay. So those sort of disconnects were being discovered. And then we could then put that into the model and say, hey, okay, what are we going to call it? Let's call it Y. Okay. So when we model it, we're going to call it that. Okay, let's move on. Right. So these things can get discovered, and there's, again, I'm a huge MBSE proponent, but engineering doesn't happen in MBSE. And engineering happens outside of that. MBSE can help facilitate the discussion, but it isn't the end of the discussion. So doing things on flip charts where everybody can see, or at least pulling everything up on a view graph so everybody can see, is huge in terms of getting the engineering ideas to flow. So this is some feedback that we got from our customer in doing this, and so and you can kind of read. I'm not going to read all these yourself, but help to organize the team's thinking when it came to system engineering, because everybody was kind of focused on their day-to-day problems, but they weren't really thinking outside of their own little boxes. They weren't, you know, they needed to get the big picture. So it really made everybody stop and pause and look at the problem together. One of the huge thing, again, as a system engineer, one of the hardest problems in system engineering is getting everybody to agree on what to call stuff. And just getting everyone, I felt like I had success because I got everybody to agree on a taxonomy: system, segment, element, subsystem. Great, because that wasn't agreed when we walked into the room. One person's system was another person's subsystem. So we got buy-in on that, which was huge. And so suddenly everybody's saying segment when they mean segment. Great. We got that, and the ontology on the data map. Okay, well, we're gonna call these requirements, and then we're gonna say they're satisfied by this, or this is produced by that. We kind of got agreement on that basic ontology. And there was a part of this project that Navy's doing and still doing. It was a pathfinder for digital engineering within the organization. So they were kind of on the hook to show that they could do MBSE implementation. And this really helped them do that. So, because again, we could model in parallel, and it's ongoing. And so and it's not tool specific. They're using multiple tools across this project, but getting them to even think about it in the same way, and getting them to understand what MBSE can and can't do for them within the project was also pretty important. So other things here, planted the seed for culture shift, clarity on the topic, getting everybody to think about the same way, alignment of the team, and so importance of really getting the team set up for success for that, and help that transition to MBSE. So simply just, a lot of organizations unfortunately think, well, hey, I bought everybody licensed to the tool. How come we're not doing MBSE? Like, well, that's, I bought you a basketball. How come you're not winning the championship? So how do we get from the tool to the implementation of using the tool effectively in the organization is what we're talking about here. So conclusions here, that ready, fire, aim approach, MBSE just isn't successful. We really got to step back and say, what are our processes? What are we trying to do? Do we have a common understanding of the project? Are we ready to go build models? To me, you almost should have a license where you're allowed to go off and do that. Do we understand how we can, where the time and tension is in the project, and use things like this workshop, this accelerated workshop, to ground everybody in system engineering principles and processes, help establish the simple things like taxonomy and ontology, and start to get a common sight picture of how you're going to approach that, and then use that to help get people focused on done. Again, I always say, question number one for MBSE is, why are you building this model? And if you can't tell me why you're building it, then maybe that's not what you should be spending your time on. What questions do you plan to answer with the model? And then I can come up with a definition of done. So at least done enough for now. No model is ever done, but what's done enough for the next design review or whatever that I have coming up here. And then what's your review process for that? Again, modeling just a model, how do I know that my model is effective? How do I know that it answers the questions I want? And overall, then I hope that'll help better support MBSE adoption across the community. So thank you for your time. Time for questions. Thanks. Sure.
Can you tell us what projects were actually implemented, NASA projects, that not just the FireSat, but an actual project?
For this discussion, we've only used this accelerator workshop, as I've described it, for this NASA class. And we've taught this class, I can't remember how many times does this. And we use this fake project, FireSat. But anecdotally, students will say they take away a lot of the concepts that we use back to their own project. One of the key ones is just saying, hey, what are the key artifacts, and can we define done for that? Because there's a concept in Agile we call technical debt, which is basically, if you didn't get it done, that becomes debt that compounds interest that impacts other things coming down the road. And that even just those sort of intellectual concepts are really valuable as people go back to their own project. Sir.
As we learned about DDSE basically this morning, how do you expect what sounds like the inevitable shift from MBSE to DDSE to affect how you present this workshop going forward? What can we keep? What needs to be changed?
Yeah, I've had lots of discussion with Warren and Steve. I fundamentally it doesn't. And so it's really more of it's more a naming convention, but I don't think it really changes what we're talking about, because we're really looking more at bigger picture of what am I trying to do here, right? Yeah, that's certainly data-driven engineering, but whatever you want to call it, I have basic things I want to be able to communicate, right? And that's, to me, system engineering, project management hasn't changed really since we built the pyramids. I mean, it's the same stuff. We call it different things, but there's the same amount of information. In fact, one of the lessons learned, and I'll call out Amanda, wave Amanda. So Amanda, actually, she helped facilitate the class we just did with NASA just about a month ago. And we took, we're always learning too. And one of the things we learned is we actually need to focus this even more. That 28 things was too many things. We need to actually get even better focus. And so that's kind of what we're probably going to do next time we think about it. Is like, okay, now let's take 28 and boil it down to like 14, because we're thinking about what do we kind of call it? The Magnificent Seven. So we're kind of like, what are the Magnificent Seven PM and SE products? Can we even focus it even more? And I think, because again, people get distracted. I'm doing a project now for a horse research lab, and they got 940 requirements, and they just got started. I mean, it's like, folks, you gotta focus. You can't focus on 940 things. So we gotta, that's great. You wrote all those requirements, but time out. Can you tell me the 10 things that are most important? Like, okay, so I don't see that changing anything in the way we think about it. So, yeah. Time for one more question. All right, well, we brought a lot of swag, so come by our booth and pick up some. We have cool little rocket flashlights. So, thanks, folks.
Thanks, So next up, whoa, like a little roar. Yeah, mute that mic. Yeah, that shouldn't happen. Yeah. All right. So next up is lunch in the Disney dining room. So we'll be doing that for the next hour, and then at 1:30 we'll convene either here or there, depending on what sessions you'd like to attend. Thanks.